So let's take an ellipse on the plane and place a point M on its boundary that I can choose where I'm going to place it, like so. Let's go ahead and also pick another point P on the same ellipse's boundary, and I can also place it anywhere. I'm going to draw a straight line between these two. There it is. It's a straight line between P and M. If I move M, the straight line moves like so. If I move P, the same thing kind of happens. Now I'm going to draw a line that is perpendicular to MP, which passes through P. There you go. So this is a thick dashed purple line. And if I animate, for example, P's position, that line moves around like so. So the natural question to ask here is, where is the instantaneous envelope of this line? Or as I like to phrase it, what's the instantaneous center of rotation of this line? And what kind of a curve is this thing sweeping? So the curve this envelope sweeps, or this instantaneous envelope sweeps, is known as the envelope of this family of lines. So this family of lines envelops this deltoid shaped thingy. If I move M around, I place M somewhere else, I'm going to be sweeping a different envelope. This particular envelope does not have a natural axis of symmetry, somewhat asymmetric. Now the first thing that you realize here is that if I vary M and I place M anywhere on the ellipse, so let's forget for a while here about this construction aids, including instantaneous envelope. If I move M around, not P but M, each position of M induces deltoid that looks slightly different from one another, right? But if you calculate the area of this deltoid, I'm showing it up here, you notice the first surprising phenomenon. This area is invariant. It's independent of the point M that generates it under the construction we just demonstrated. Okay, now this is the first phenomenon. A second phenomenon you're going to notice is that this envelope is tangent to the ellipse at a single point and intersects with it at two other points. Let's just focus right now at the point of tangency. So let's animate this so we can observe this tangency a bit better. So the point of tangency, for example, is over here right now. It turns out this point of tangency is happening at the only point along the boundary of the ellipse whose normal to the ellipse is pointing in the direction of M. So if I draw that MP line again, let's go ahead and light up P. Let's draw the line MP again, and let's draw the normal at P. The normal of the ellipse to the ellipse at point P points downward like this. But if I move P around such a way that it approaches that area where the deltoid is touching the ellipse, you're going to see that you get this kind of a beautiful alignment here. So the touch point is happening at the one point along the boundary that has this kind of a property. If I move M around a little bit, I'm going to get a different touch point, for example here or down below. Here you get kind of this fast transition from one point to the other. Okay, if I get to this point over here, I'm going to get the same property if I move P so that it approaches that point. So I think I'm going to have to turn P all the way around. I get this normal alignment again right here. Okay, so that defines that one point of tangency. Very well. Okay, so let's keep going with the phenomena here. Let's move M around so the deltoid is up here. Okay, so this is an invariant area deltoid. The other thing you can do with it is you can compute its center of area. Here it is. So I can take this whole area, do those double integrals, and get an area centroid. And I'm representing this guy as C2. So as I vary M, that area centroid is moving around. What curve is this thing sweeping? It turns out it's sweeping a perfect ellipse. So the locus of that center of area is a perfect ellipse, which is a tad bigger. It's a tad bigger than a rotated copy of the billiard itself. So here's a rotated copy of the billiard itself, 90 degrees rotated. You can see that the locus of that area centroid, represented as C2, is an ellipse, concentric, axis aligned, but slightly bigger. If I change my aspect ratio, change my ellipse aspect ratio, those two curves approach each other, the locus, the dashed purple locus. As the ellipse becomes more and more eccentric, they are more distanced from one another, but as the ellipse approaches the circle, you get this phenomenon. Okay, now let me go back to the area of this deltoid, because I forgot to mention a very interesting and pleasing phenomenon. So I'll turn off the locus of C2 and the rotated copy of the billiard. I told you that the area of this deltoid is invariant. If I pick a specific kind of aspect ratio, for example, if I pick this aspect ratio to be the golden ratio, which is 1.61803, give it or take some digits. So I'm going to make this aspect ratio, the major by minor axis of the ellipse, be exactly or pretty close to the golden ratio. It turns out that the invariant area of the deltoid is exactly 1/2 the area of the ellipse. So magically, at this aspect ratio, at this golden aspect ratio, you get area invariance for the deltoid. Of course, the ellipse is stationary, so its area doesn't vary, but one area, the ellipse over the deltoid, is 2. Another magic aspect ratio is when this A over B of the ellipse is equal to square root of 2. Let's go ahead and try to recover from this error. There it is. So when it's square root of 2, and I animate M, I still get an invariant deltoidal area. However, now the ratio of ellipse to deltoid area is 4. So just remember, square root of 2 gives me a ratio of 4, and the golden ratio gives me a ratio of 2. That's pretty nice. So let's go back to something that is neither. For example, 1.5. It doesn't matter. It's between the two. I don't get an exact integer here as a ratio. I get 2.88. Very good. Now, I want to now talk about the triangle that can be defined by the 3 cusps of the deltoid. So here's a triangle. Let's go ahead and animate this again. And let's look at the area of this triangle. Here's another invariance. The triangle defined by the 3 cusps has invariant area. Furthermore, the average of its 3 vertices, i.e. its center of mass, is congruent with the center of area of the deltoid. So I'm saying the center of area of the deltoid, C2, is congruent with the barycenter of the triangle defined by the 3 cusps. And this is dynamic. That's pretty pleasing. Oh, I forgot to mention to you guys one thing with respect to square root of 2 aspect ratio. When we pick this particular aspect ratio, a very pleasing phenomenon happens. At this particular configuration, when M is one of the vertices, one of the cusps of the deltoid passes through or just pricks the center of the ellipse. You can see here that's going to happen when M crosses over to the other side. You're going to get the same phenomenon here. So I just exactly touch that point. And this only happens for A over B equals square root of 2. That's pretty nice. Okay, so there's a few more phenomena here that I want to cover. Let's go ahead and now talk about what are the points on this boundary that are associated or generate the 3 cusps. I'm going to go ahead and draw these so-called preimages. If I draw each cusp with a color, red, green, and blue, I'm going to say that this red cusp is associated with this red boundary point, and so forth for the green and for the blue. Let me just explain to you guys what I mean by associated. Let's bring P back, and let's draw that line between M and P again, and let's draw a perpendicular line to P. Okay, now let's draw the instantaneous envelope. Instantaneous envelope is here. It's not quite at the cusp, but it's close to the cusp. So if I move P around just so that it reaches that preimage on the boundary right here, at this point, my instantaneous envelope is right at that cusp. So whenever P crosses one of these 3 points, red, green, or blue, my instantaneous envelope is going to be at one of the cusps. Let's watch that. So here's P approaching the blue, and E is approaching this blue cusp. It just touches there. Now P is going to leave blue, and it's going to start sliding toward green. My envelope is sliding up toward green. and I get to the next so-called pre-image of that green cusp on the ellipse boundary. Let's just let P reach red, and then we're going to talk a little bit about those 3 points. So there it is, we're reaching P, and the envelope is touching red. That's all nice. Okay, so what do I want to do now? I'm going to turn off a few of these things that we don't need anymore. The deltoid triangle. I'm going to turn off these construction lines. There you go. I'm just going to leave the deltoid. I'm going to turn off the instantaneous envelope as well. We don't need it. So I have 3 dots. I think I need to draw the deltoid triangle so I can see the 3 colors up here. So the 3 cusps are associated with 3 points on the boundary that produce an instantaneous envelope at the cusps. Now, the natural thing to do here, first of all, is to connect red with red, green with green, and blue with blue. Now, this is what happens when you do that. If you just do the simple connection, cusp with its preimage on the ellipse, cusp 2 with its preimage on the ellipse, and the third cusp you do the same, and you just extend these lines to infinity, you notice that dynamically these lines concur exactly at the area center of mass of the deltoid. And again, this is a rather pleasing phenomenon. We've proven it algebraically, but we don't have an intuition as to why this is happening. Another intriguing phenomenon is that whenever the center of mass of the deltoid crosses the ellipse, it does that through a vertex or through one of these 3 preimages. So notice that. So x2 just crossed it through red. It's going to come down here and cross through the blue preimage. I'm just looking at x2, and now it's going to cross the ellipse. I can draw its locus because it's actually going through an elliptic locus. So x2 will enter the ellipse always whenever one of the preimages is at that point. So here's you have the red preimage. Likewise, cusps will enter and exit the ellipse also through their preimages. So if I animate this, let's track green. Let's track this cusp here. Let's see what it does. So it's going to exit the ellipse at any time, and it's going to exit the ellipse when it is congruent with its preimage right there. The same thing is going to happen to all 3. So for example, we're going to get now blue is inside the ellipse, right? They're inside the ellipse one at a time. Let's call this guy green here. So green is going to exit the ellipse when it passes through its preimage right here. Okay, so that's another very interesting phenomenon. So you have concurrence, you have these congruences, we have area invariances. Let's now cut to the chase to the very last set of phenomena. Let's go ahead and turn off the locus. Let's turn off the deltoidal center of mass, these concurrent lines, and even this triangle. Okay, so now I want to connect the 3 preimages, which are here, and form a triangle with them. So there it is. So I've connected the 3 preimages, so we can associate them by color with the 3 cusps. I must draw this dotted triangle, and I'm going to animate M so we can see these systems moving around. So I have a triangle that is defined by the 3 preimages. If I do a first calculation, the average of these 3 preimages, i.e. the centroid, remember that the vertex average is equal to the area centroid of a triangle, its centroid is invariantly stuck on the center of the ellipse. So I'm drawing x2 using Clark-Kimberlin's notation here, saying that the centroid of this dynamically varying triangle is on the center of the ellipse, and it's stationary. Another thing that you notice is that if I compute the area of this triangle, So over here, area of the preimage triangle, it is also invariant. So now I have 3 invariant areas if you don't count that of the ellipse, because the ellipse is by definition stationary. I have an invariant area of the deltoid, I have an invariant area of the triangle formed by its 3 cusps, and I have an invariant area of the triangle formed by the preimages of the 3 cusps. It's just invariant, it's right there. Now, because its barycenter is stationary, and the original ellipse passes through its 3 vertices, we can think of this ellipse as a barycenter or an x2 centered circumellipse. Okay, and this object is also known in the world of triangles as the Steiner Circumellipse. The Steiner Circumellipse is the smallest of all, in terms of areas, the smallest area circumellipse to a triangle. Now, the next thing we did here, because we were so curious, was what is the caustic of these 3 sides? So we calculated the caustic of these 3 sides. It's another ellipse. There it is. It's shown dotted. And we found that algebraically this ellipse has its major and minor semiaxes equal to exactly half the major semiaxes and minor semiaxes of the Steiner. So this object here also has a name. It's the Steiner Inellipse, which is also known to have the same properties, half the semiaxes, and it's the smallest area inellipse of a triangle. So the smallest area inellipse of a triangle, inellipse meaning that it's tangent to each one of the 3 sides, is centered on x2, the barycenter. So that was pretty pleasing as well. So that's our final system. We're looking for envelopes of perpendicular lines, and we found the Steiner Circumellipse and the Steiner Inellipse, i.e. this family of orange triangles. This family of orange triangles is a Poncelet family because it is inscribed in an external conic and it circumscribes an interior conic. It just so happens that these 2 conics are concentric and axis aligned. Thank you very much.